Okay, so as a continuation from uh, lecture 6, part 3, now we're going to go into the details. So how do we combine this set theory with discrete time system models? So that's what we're going to discuss in this lecture. So we're going to start with what we call, again, discrete time system models. And then I'm going to explain an example of a simple machine. And we are going to discuss also how is this tied to state transition diagrams. Those causal loop models that we discussed at some point, those are going to be back at this lecture. And then we're going to discuss what are input state and output trajectories. And finally, we're going to talk about system experiments and performance indexes. So let's talk about discrete time system models. This concept of a discrete time, or simply discrete system model, refers to an open system with input, state, and outputs. So again, this could be anything like a machine or road that you're trying to represent. So the outputs are produced as a result of the input to the system and the dynamic interactions of the elements inside the system. Discrete time refers to the time scale being discrete, so time will go from 0 to 1, from 1 to 2, and so on. We are not going to be looking at fractional time points. We are going to look at integer time points. So mathematically, a discrete system model is a 5-tuplet, which consists of the following 5 sets. Okay, so we have the following function. We have a function z, and we have 4 sets. The state set, the input state, the input set, the output set, the state transitional set, and the readout function set, which are, the names are listed here. If we want to represent this as a block diagram, again, we go to that black box representation. We have the following. We have the input set, which is basically representing all the inputs that your system must handle. And then inside we have some transition happening in which you need this state function or this state set. The state set is going to, if you're looking at the machine, for instance, you're going to have multiple states. The machine could be idle, the machine can be busy, the machine can fail, the machine maybe is under maintenance. So those could be different states for your machine. We have state transition function, which basically is going to use the information from the input and the current state to see if you need to change states in your model. And the readout function basically tells you if by changing states you need to generate some type of output for your model. So for instance, if you are looking at the HVAC system, maybe if you go from one level of temperature to another, you might need to trigger a change in your state. Maybe you need to go from off to on, but also you have to send a message. So maybe you have to tell the user that the temperature is moving from this point to this point. That's what we're trying to represent here. So if the number of states and inputs are sufficiently small, the functions mz and rz can both be defined by either a state transition table or a table. Otherwise, these two functions or these two sets or functions are defined either as a set of ordered pairs or in terms of functions. The set of theoretic models are not necessarily finite state machines. A system Z is finite if and only if the state functions, the input function, and the output functions are finite sets. So here we have some descriptions. So by definition, our state function is a non-empty set, the input set, and the output set. So we have defined all these three already. This state transition set belongs to a set of functions. The functions are defined here. So it depends on what type of input you're receiving. So if your input is non-empty, meaning that you are gathering input, that state transition is going to happen, and it's going to look at this cross matrix product of the states and the inputs, and the range or the output is going to be a change of state. RC is belongs to a set of functions denoted by the empty set and the function, which has the domain, which is the state set, and the range is going to be the output set. So if you are getting some information, if your output is not empty, then you're going to look at this function. Otherwise, this transition is going to be empty. The time scale of the discrete system, Z, is denoted by TC, and is denoted as a set of integers. So the time frame, again, is this timeline that we are following, and we are going to track what are the changes of the system at any time. However, real models exist in real time. Discrete times are basically, again, an assumption that we are making to make our models easy to represent. Discrete system model exists in discrete time, which means that the interpretation of the model must include the relationship of model time to real time. So again, we are looking at changes at these integer time periods, but we need to find a way to represent that real time with our discrete timeline. The discreteness of the timescale implies other approximations. Our arrivals between t and t plus 1 can be assumed to have occurred as input to the discrete model at time t. Okay, so we are assuming that if something happens between t and t plus 1, that arrival will be considered as arriving at time t. All outputs or all outputs between t and t plus 1 can be assumed to be produced by the model at time t plus 1. So inputs are going to be considered at t, outputs are going to be produced at time t plus 1. So let's look at one example. This is the model of a simple machine. So an example of a discrete system model M can be given as follows. So this is what we're going to call a machine in terms of this example. So a machine, I'm going to call this model M. It's going to be modeled using the following sets. So we have the state set, the input state, the output set, the state transition set, and the readout function for our model, where we're going to have the following states. So the states are going to be 1 and 2. The inputs are going to be 3 and 4. The outputs are going to be defined as 5 and 6. And then we are going to have a function that is going to be used to define the state transitions. So that function is defined as double F, which is the cross product of the state set and the input state. And the function is going to generate an output, which is a change or a change of state. So to define that set, let's look at the following. So we're going to have this pair 1, 3, with state 1, we're going to have the following: 1 and 4, 2, 2, 3, 1, 2, 4, 1. So what this means is the following. Again, here we have the cross product. So the first one represents the state set, and the second one represents the input. So what this is saying is, if you are in state 1 and you receive an input 3, then you're going to stay in state 1. The second one says that if you're in state 1 and you receive an input of type 4, then you're going to transition to state 2. The third one says if you are in state 2 and you receive an input of type 3, then you're going to transition to state 1. And the last one says if you're in state 2 and you receive an input of type 4, then you're going to go to state 1. So this function, again, what it's doing is representing the changes in your system. Changes in terms of state. Okay, so this is our NM function. And then finally, we have the yes, go ahead.
Can you explain how it translates again? It was like if you're starting at system or at
yes, yes. So these are your states, and this is going to be more clear when I draw a state transition diagram. So these are your states. So meaning that your system will be in state 1 or state 2 all the time, in one of those two. And you're going to be receiving these inputs, 3 and 4. Okay? So what this transition function is saying is, if you're in one state and you receive one of these inputs, what's going to happen? So you start with Sn, which is your state. Im is your input. So the combination of these two, or the cross product of these two, is going to generate a new state. Okay. So if you're in state 1 and you receive input 3, then you stay in state 1. Okay. Okay? And the rest is the same. Good question. And then we have the readout function, which is the following. So what this is saying is, if you are in one state, then you are going to generate an output of certain type. So for example, what this is saying is, if you're in state, after this transition, if you're in state 1, then you're generating an output of type 5. After this function, if you're in state 2, then you're generating an output of type 6. Okay? So let me make a note here to make it more clear. So note the functions NM and RM are written using ordered pairs. So NM is represented as state, input, and then state, and RM is represented as state, output. Okay, so this is just a note to help you remember what this is representing. Okay. Any other question at this point? So now we're going to give some meaning to these numbers. Oh, sorry, so that's already there. Okay, so consider a practical interpretation of M. System M might be thought as a model of a machine. So two states, state 1 is idle and state 2 is busy. So if we consider 1 and 2 along those lines. And two inputs, input 3 is null, and input 4 is request for service. And two outputs is 5 is nothing, output 6 is service. So when a machine receives a request for service or input 4, it assumes the busy state, state 2, for exactly one time period, after which, regardless of the input, the machine will return to the idle state, state 1. The machine recognizes a request for service input 4 only when in the idle state, state 1. In the idle state, state 1, the machine outputs nothing. In the busy state, state 2, the machine would output service. That is what this model, that is not clear now, of the overlapping, is representing. Okay, this is the description. If you're going to give them those numbers some meaning. So system model M can now be expressed as follows. Okay, so here's the translation. So the states are going to be idle and busy, so 1 and 2. The inputs are going to be null and request, 3 and 4. The outputs are going to be nothing and service. The state transition is the following. So if you're idle and your input is null, then you stay idle. If you're idle and your input is request, then you go to busy. If you're busy and your request is null, then you go back to idle. If you're busy and your state, your request or your input is a request, then you go back to idle. The output readout function means that if you're idle, you are not outputting anything. But if you're busy, then your output is service. So we went from defining this in terms of numbers. If we gave some definition to those numbers, and now we can see better what the model is trying to represent in terms of a machine. So we can also represent this behavior using state transition diagrams. So if you remember the causal loop models, these are very similar to causal loop models. A diagram that depicts the behavior of a system in terms of state transition is called a state transition diagram or state chart. Each state is represented as an oval with a state transition between states, indicating by digraphs or arrows point in the direction of the state change. So for example, we can draw a state transition diagram for system model N and describe its operation. So the ovals again are representing the states of the machine. So we have two states in this case. And then we can see the connection between the changes in state. So this arrow right here that is staying in the same state basically represents that if you receive this type of input, nothing is going to happen. But if you're idle and you receive a request, then you're moving from idle to busy. And if you're busy and you receive one of these two types of requests, or a request or a null input, then you're going back to idle. It's the same representation of what we describe as a model, using the sets and the functions. To capture the state transition and the system outputs, a readout table is used. The readout table has the following columns. A column for the state, which is this one. So we have two states, idle and busy. A column for each input, P. So we have two inputs, P3 equals null and P equals 4 request. And a column for the readout output function, which is here with readout function. So we have two readout functions, nothing and service, so 5 and 6. Okay, so this is the readout table for system N. Another way to represent the behavior of the system. Okay, so let's talk about input state and output trajectories and why is this important. An input trajectory for system Z is a non-empty string of elements of this input set. So remember your inputs, you have 3 and 4. So now we're going to test our model. If we give this many inputs, let's say we run this for 1 day, and during this day we're going to have this many inputs. We want to see how the model is going to represent the behavior of our system. So an input trajectory is a function of time. Examples of input trajectories for M are here. So CNS is a constant function, which means that you're going to be receiving 3s all the time. And then we have constant 4, and then we're going to have another one that looks like this. Other examples are trace of voltage inputs to an electrical component, or set of all emissions to an hospital over a given time. So it's anything that can represent the behavior of the interactions with the outside world. So if you're looking, for instance, at the attendance of this classroom, I mean, some of you will arrive at before time, some of you would arrive on time, some of you would arrive after the start of the class. So if you're trying to represent that behavior, then you can link. So student 1 arrive at this time, student 2 arrive at this time, student 3 arrive at this time. That is an input trajectory for the attendance in this class, for instance. And if you look at the machine, let's say you're producing a certain product, so you want to know how many parts and at what time each part is arriving to that machine, and then you want to represent the behavior of that machine. So a state trajectory defines the state of the system at any time. So now that you're going to have that information of the inputs, this string of inputs, how is that affecting your states? So the state trajectory is going to represent that. So the state trajectory is going to take into account all that input string, and it's going to look at the states in the set of states and the time in the set of time. Then the state trajectory of the system Z with respect to the input trajectory F and the initial state X is denoted by this function, STZ, which uses that F that is coming from the input trajectory and X, which is the state or the current state of the system. And that's defined as follows. So that state trajectory is going to be defined again as based on time and the state. So Y is going to represent the new state. So if you're looking at time and the current state, that's going to be defined here. And Y is going to change depending on what time you're looking at from the input trajectory. So X is going to be the state at time 0. Otherwise, you have to look at the combination of time and the current state trajectory to know what's the next state of your system. The state trajectory is interpreted as the state of the system Z at time t given an input trajectory F at the initial state X. Observe that the state trajectory is a function. Okay, so this state trajectory is going to be a function with a domain and a range. So how can we use that to represent our behavior? So maybe this is going to make things clear. So this is what we have. This is an example of state trajectory for system M. So we're going to look at time. So this is the time period. So we go from time 0 to time 8. And I'm going to generate some inputs. So I'm going to tell you, okay, this is the input that the system is receiving at each time period. And then based on those inputs, you're going to have to tell me what is the next state for your system. Okay, remember that we're going to have an initial state. So an initial state is defined here. On the state column, you see this STM. That STM has an X. That X is telling you what is the initial state of your system. So in this case, we are starting our system in state 1. Okay, so I'm going to give you some inputs here. So let me define some inputs. 4, 4, 4, 4, 4, and then 3 and 3. So this input is given. So this, I'm telling you, this is what's happening at each time period. So now based on that, I want to know what is the next state of your system. So remember, this state transition diagram is telling you the transition for your system. So if you're in state 1 and you receive an input of type 3, then you're going to stay in 1. If you're in state 1 and you receive an input of type 4, then you're going to move to state 2. So in this case, you're starting our system. So this is our initial state. Okay. So this is coming from here. This is our initial state. Okay. So from there, we're going to start completing this table. So if you're in state 1 and you receive an input of type 4, what's going to happen to your system? You're going to move to state 2, right? So if you're in state 2 and you receive an input of type 4, what's going to happen to your system? You go back to 1, right? If you're in 2, like here, and you get an input of type 4, then you go back to 1. If you're in 1 and you receive an input of type 4, then you go back to 2. If you're in 2 and you receive an input of type 4, then you go back to 1. If you're in 1 and you receive a type 4, then you go to 2 again. If you're in 2 and you receive an input of 4, then you go back to 1. If you're in 1 and you receive an input of 4, then you go back to 2. If you're in 2 and you receive an input of 3, then you go back to 1. And if you're in what will happen next? If you're in 1 and you receive an input of 3, what will happen? You stayed in 1. Correct. Okay, so I want you to be clear with this table. Most likely you're going to see this in the exam. So how do you complete this table? You have some time periods here. The input is given. This is given, the initial state. So that initial state, that first state has to come here. That's your first state. And from there, you move from this state, you get this input, you move to the next one, this input, you move to the next one, until you complete this state. So this is representing the behavior of the system for a time period. The output trajectory of the system Z is determined by the input trajectory and the initial state. It is denoted by OTZ, which is a combination of the functions or this input trajectory and the initial state, and it's defined as follows. So again, the output trajectory is going to take into account the state transitions and also the input trajectory and the initial state. So this output trajectory is also a function. So going back to this example, let me, again, one more time, represent the system. So 1, 2, from here to here, you have a 4, from here to here, you have a 3, then a 4, and you stay here. So the input that is given is 4, 4, 4, 4, 4, 4, 4, 3, and 3. And this time we are starting our system at state 2. So this is 2. And again, we're going to go through the same process. So that's given, and I need you to complete this portion. Okay, so this is going to look similar to what we did on the previous table, with the only difference that now you have state 2 as your initial state. So from here, we're going to do the following. This is 1, 2, 1, 2, 1, 2, and then 1, 1. The important thing now is that we are going to also complete this output readout function. So if we are in state 2, that means that the service has been completed. So we are going to generate a 6. If we are state 1, then nothing happened. State 2, service is completed. So the same will apply for every 2. And then the output for the 1s are going to be just idles. So 6 is again representing service completion. Five is representing that the system is idle. Okay, so remember that the readout function is represented as follows. So 1, 5, 2, 6. Okay, and that the first number represents the state and the second number represents the output. So systems experiments. We shall assume that with respect to the use of system models, that the modeler, in this case you, is omnipotent and omniscient, meaning that you can represent or you can do or run any experiment that you want. The modeler can do what they like with or withdraw to the system and observe anything they like in terms of the model. The modeler can place the model in any state they like, generate any input trajectories, and observe the input state and output trajectories as they dynamically produce. Computers make this possible. However, time and money limit the activities of the modeler. So you're going to have, if you're working for a company, you're going to have these many hours available in a day. So time is becoming your constraint most of the time. So performing an experiment on the system refers to placing the system in a state, generating an input trajectory, and letting the system operate on that input trajectory until a specific time. The set of system experiments for system Z is denoted at EXZ and is defined as follows. So the experiments are going to look at the input trajectory, the state, and the time. How long are you going to run this for? A system is a dynamic phenomenon. The definition of system experiments given above does not quite capture the idea of the system dynamics. A triple of the form F, X, and T specify a system experiment instead of being a system experiment. The dynamics of the system models are exhibited in system experiments with the following interpretations. Suppose that F is an input trajectory for the discrete system Z. Then for each time values S, f of S is an input that system Z will experience at time S. The system Z is initiated in state X at time 0. At each subsequent time value, inputs are generated according to the input trajectory F. F, the state transitions, and the output trajectories are observed from time 0 to time t and are recorded in the system experiment data table. So, the omniscient and omnipotent modeler of the system knows that the following. So at time 0, we have this initial state in this readout function. At time 1, then we're going to use that initial state to see what's going to happen in terms of the next state for our system and what will be the output for the system. And that will continue. Now, if we are going to time 2, we're going to use that information from the previous time period to represent the next behavior of our system. So that's what's denoted in this table. You see, you start with the initial state, x, this coming from here, and you're going to see what is the readout function based on that state. But from this state to this state, then you're going to take into account what was the input, f of 1, and the previous state, which in this case is x, to represent the next state of your system. And that behavior is repeated after each time period. So this is what we call a system experiment data. Okay, so here we're going to look at the following. So I'm going to give you the next this input trajectory. Okay, and we're going to look at the function. So this is 3, 3, 3, 4, 4, 4, 4, 3, 3, 3, 3. So based on this, you know that the initial state is going to be 2. That's coming from that state function. That's your initial state. And then that's given. So using this information, I'm going to complete the rest of the table. So that's why I'm using a different color. So I'm going to use this light blue. So red is given. The rest you need to complete based on the information that was given. Okay, so we are going to move from, so we are in state 2 and we are receiving this input. So that means that we are going to go to state 1. We are in 1. So we are going to state in 1. We are in 1 and we are stating 1. Now we receive 4. So that means that we are going to 2. We receive 4. So that means that we go to 1. We receive 4, that means that we go to 2, 4, that means that we go to 1, 3, we stayed in 1, 3, we stayed in 1, 3, we still in 1. Okay, so these transitions are based on this transition model. If I'm in 3 and I receive an input of type 1, then I'm not changing state. If I'm in 4 and I receive any type of input, then I'm transitioning to state 3. State 1. Okay, and the readout function is pretty simple. Once you have the states transitions, then you just have to look for whether or not you are in state 2 or 1. And based on that, you're going to generate an output. So in this case, this is 6, 5, 5, 5, 6, 5, 6, 5, 5, 5, and 5. So if you're transitioning to state 1, then these are 5s. If you're transitioning to state 2, your readout function or your output is going to be 6. So the idea now is, how do we use this for an experiment? How do we use this information? What are we trying to capture here? So typically the raw data displayed in the system experiment table must be summarized in order to be useful for the evaluation of the performance of the system. So some examples include, we can count the number of times a certain index is performed. We can look for minimum, maximum, average, median, standard deviation for all these performance. The set of system performance indexes for system Z is denoted by PIZ and is defined as the set of all functions defined over the experiments. For our example, system M, our PIM includes the following. Number of times a request is made, that is, when the system M received an input 4. Number of services rendered, that is, when system M output is 6. Minimum, maximum, average, and standard deviation values for the above indexes over a specific time interval. Okay, so we can compute all of that with this experiment table. A clear distinction must always be made between a system model and its interpretations in terms of a real system. Okay, so going back to this, we have the following 2 here, okay, and I want you to complete this table, and you're going to answer these 3 questions. If you're able to do that and submit it with a piece of paper, then I'm going to give you 5 points for the final exam. Okay, so I'm going to stop my lecture here.